Hey everybody, welcome back to Organic Chemistry. In this video, we're going to go over Sn2, substitution nucleophilic bimolecular. And what we're going to do is we're going to learn a lot about different characteristics that make up the substitution reaction, but our focus is going to be on the Sn2. Before we do that, we should start with a quick introduction and a general idea of what this means to be substitution and nucleophilic, and then we'll dive into the Sn2. So this video is going to be probably about the same length as the first video, which is probably around 2 hours or so. And you should definitely pause in between. Don't just run through the whole video. Take your time, look it over, get acquainted with the material, take some breaks, drink some coffee, and keep going from there. But the idea of this video is to really focus in on Sn2, but use it as a model to understand some of the other characteristics like solvents and nucleophile types and so on. So this one is a little bit long, but the Sn1 video that follows will be a lot shorter because we're going to do a lot of the heavy lifting in this video right now. Okay, so these are the sections. There's only 4 sections, and we're going to wrap up with a whole bunch of problems to do together. Okay, so let's get started. The first thing I want to talk about is an introduction. Okay, so let's go ahead and just do a quick introduction. Now, the idea is that we have something called a nucleophilic substitution reaction. Now, what is a nucleophilic substitution? Well, we know what a nucleophile is. All right, so that's what's going to come into something and give electrons, right? Remember, nucleophiles are looking for the nucleus, the positive source, and it gives electrons. So we're going to have something like the following. Let's say we have an R, which is representing a carbon, and we have X, which represents a halogen. Now that's going to react with some nucleophile, and I'll write just Nu, and at the end of this reaction I'll write Nu minus. It becomes Nu attached to R plus X minus. This is a general idea, okay? So R represents carbon. We know that from the previous exam 1 actually. The nucleophile, we know it. Minimum requirement for a nucleophile is that it has a lone pair. That's it. It doesn't matter if it's negative or neutral, but it needs a lone pair. Okay, and X equals halogen, right? So X is nu. That equals halogen. It could be a Br, a Cl, I, or F. We'll actually learn other things that could be X, but for now we're going to strictly stick with halogens for now. Okay, now this is a substitution because we're swapping out the halogen for the nucleophile. We're doing a substitution. We're substituting one for the other. Okay, now this right here is known as a substrate. The substrate is the alkyl halide for this chapter, but more broadly, a substrate is the molecule that you're most concerned about. It's the one that we're going to do the work on too. So the nucleophile is working on that substrate. It's going to break the bond and form the bond. It's going to do stuff with the substrate. Okay, so the substrate is our focus. Now at the end, notice that there's this halogen. This is called a leaving group, or Lg, right? Lg. The leaving group is the one that leaves the substrate. So the halogen is going to leave the substrate, and the nucleophile is going to come into that substrate. And this is the terms that we need to be familiar with. Okay? Now, the next thing I want to point out is that when you think about how this can happen, it actually can happen 2 different ways. Think about it. One way that this can happen is where the substrate has its leaving group leave while the nucleophile comes into it at the same time. That's known as an Sn2. So let's make that general overview. For an Sn2 reaction, the leaving group and the nucleophile react at the same time. So if they react at the same time, one comes in while the other leaves, that's called an Sn2. But for an Sn1, it's different. The leaving group leaves completely independent of the nucleophile, and once it's gone, then the nucleophile comes in. That's known as an Sn2. So the leaving group leaves before the nucleophile enters or bonds to the substrate. Or yeah, let me write bonds. It's probably better than enters. So a nucleophile bonds to the substrate. And so that's the idea of an SN1. SN1, things happen at different times. SN2, things happen at the same time. That's the difference. This video is all about SN2. We're going to focus in on the general mechanism, its kinetics, and then we're going to talk about ways to make it faster. Okay, different influences that will change the rate of this reaction. Okay, that's what we're going to do. All right, so this is our general overview. For this video, we're doing SN2. So the next thing we have to do is we need to talk about the kinetics of the reaction. So remember, the kinetics is the rate of the reaction. Now, what that means is that the kinetics tells us how fast or slow the reaction is going to be. And remember in the previous video, we discussed different ways that we can manipulate that. We could raise the energy of the reactant. We could pull down the transition state. These are things that will allow us to make the reaction faster, right? And we're going to learn how to do that in practice in just a few. But for now, let's come up with the rate itself, the rate law. And so the rate is equal to the rate constant times the concentration of both the substrate and the nucleophile. So they are both important for this reaction. Remember I just said a moment ago that for an SN2 it happens at the same time. That means there's a dependency on both of them because they have to react at the same time. So the rate of this reaction is completely dependent on both. So we have RxNu becoming RNu plus X minus. The rate depends on this one and that one, both of them. That's the rate of this reaction. So this is a bimolecular reaction, right? Remember, bimolecular, what that tells us is what the system looks like during its transition state. So during that important transition where we don't know how to isolate or observe it or do experiments on it, we come up with some analysis and it's bimolecular, meaning there are two things involved during that hill when you go to the top of the hill. Okay. So that's the kinetics. That's what we're going to deal with in the SN2 reaction. So let's go on to the mechanism. Now, an SN2 reaction, again, is what we call a concerted reaction. A concerted reaction. What does that mean? Well, a concerted reaction means that everything is happening at the same time. Think of a concert where you have all these different instruments playing at the same time. And that's what it's meant by concerted. When the nucleophile is coming in, the leaving group is leaving from that substrate at the same time. So we say it's a concerted reaction. So what that means is that this reaction has only one step. It's a one-step process because everything's happening at the same time. It's concerted. Now another thing that we're going to find right now, and then we'll illustrate out the reaction, is that it's known as a back attack reaction. So when the nucleophile comes in, it comes in opposite of where the leaving group is leaving from. And we'll see that in just a moment. And the last thing I'm going to say here is that it goes through what's called an inversion. These are the key characteristics of the mechanism, and we're going to draw that out right now. So imagine if I have, for example, I have a carbon, and I'm going to draw it in its wedge and dash form. So I have this perspective drawing, and let's say a BR is right here. And these are H's, right? We don't care. They're just H's. So actually, we can have an H, we can have a D, and we can have a T. So just to show a difference, but I don't want to make it anything but H's here. So here's my starting material, and I'm going to add to this hydroxide. So hydroxide is my nucleophile. I'm going to draw it down because it gives me more room instead of across. So here are the two reactants that I'm starting with. Now, the hydroxide is our nucleophile, right? And the alkyl halide with the D and the T, remember those are just isotopes of hydrogen. That right there is my substrate. So this hydroxide is going to come in while the Br is leaving. So this Br is going to leave, take the electrons and leave. That creates a positive carbon. But while that's happening, this hydroxide is coming in. Notice how I draw it coming in. It can't come in from the same side as the Br because the Br is going to have electrons. It's going to repel the hydroxide. They're both having electrons. They're both rich in electrons. So you can't...